Hi, welcome to the Introstat lecture series. And we are in the unit testing hypothesis. And this will be our last lecture. This is lecture number 9. We're going to talk about the hypothesis testing for the two-paired population means. In the lecture number 8, we try to compare the means between the two populations. And those two populations are the two independent populations. And now in the lecture number 9, we're going to talk about when we try to compare the means, and those means are the two paired populations. Okay, let's go ahead and get started. And let's go to our lecture notes. And so let's take a look. What do we mean the pair data here? Okay, so the pair data that means is when the observations okay, so these observations are collected okay in one group are naturally okay related to the observations in the other group. Okay, so what do we mean? That means, for examples here, right? So like if you want to test a new pain reliever drug, so you want to see how long take this drug to relieve the pain. So you have one, you choose like several patients here. So the first, you give this patient an old pain reliever medicine. So you record how much time, it takes to get this patient to relieve the pain, right? Then the same group, right? So the same group, and then the next time, you give the same patient the new pain reliever medicine. And then you record how long it takes to the new one to relieve the pain here. Okay, so for here, as you can see, you have two sets of the observations, right? So you have two data sets here, and the black one and the red ones here. But these two, they are really related to each other. They all related to what? They all related to the same population here. So it's the same people. It's before, sometimes we say it's before, after here, or new and old here. So this is a different, like when we talk about the two populations mean test, right? So the same things here, if you do here, you said, okay, I will take several patients, right? In this, let's say in the hospital A, and then you give them the old pain reliever drugs here. Then you record how much time it takes for them to relieve the pain. Then you take another populations here. Let's say this is from the hospital B here. Then you give them the drug, the pain relief medicine. Then you record how long it takes to relieve the pains here. Then you can compare, all right? So you can compare. So here you have two sets of the observation as well, right? You have the black one and the red one. But these two are from the two populations, right? So this is from the population A, from the hospital A, and this one is from the hospital B here. So these two, they don't have the relation, right? So this is independent. This is hospital A, this is hospital B. So they don't have a relation. You still can compare, you still can compare the average, the time it takes to relieve the pains, right? But those are the different type of the the mean comparison. Like for this ones here, you only have one. The pair, that means you only really have one population. Then you are trying to compare the before and after effect or new and old effect. The reason why you do this way, because you have the same basis here. So you can really, you can really kind of observe the differences, right? Now you don't need to worry about the, like the patient-to-patient differences here. Okay, so this is what we call the pairs here. So the way we get the pair data, all right, we have two ways to get a pair data. Okay, so the first way is when pair data is from an experiment. Okay, so for the from experiment, like we talk about, for this experiment, we specifically choose several patients. Then one time we give them the old medicine, one time we give them the new medicine. Then we want to see, the new and the old medicine to the same patient, are they going to be, the differences or not? So the pairs here, right? So the pairing in here is a type of we call this the blocking. It's a block. Okay, so that's why we call this a blocking here, right? So that's why we said, if you did it on purposely, you use the experiment to specifically control the experiment. So you want to see the differences, because I do know the pain relief medicine to different person might act differently, right? So that's why, I know the blocking effect exists, but I cannot control that. I really want to only control the differences between the new and the old drugs. So like it may take the patient A, like 8 minutes to relieve the pain for new old drug, and then for new drug it takes 6 minutes. But for the B maybe the pain tolerance is a little bit low, so it takes like the B maybe 12 minutes to relieve the pain. Then for the new drug, this one's here may take the 10 minutes here, right? So the differences here is the same, but from the patient to patient, we do know those have the differences here, right? So that's why, we know the patient to patient are going to have differences. So I don't really, I know the differences, but I cannot control. So in order to find the effect for just the new treatment and the old treatment, so I use the pairs here. And also the pair data can arise from what? We call it the observation study. So what is the observation study? That means I'm not doing specific experiment. I just collect the data and observe the effect here. All right. So this one's here. So this type of the study, we call it is kind of the form, right? So of what? Of the matching here. Okay, so I want to see, from here, like are they matching, and so these differences is significant or not? Okay, so that's that's what we call about the pairs here. Okay, so for the pair data, really, you have two observations, but what is the things we concerns here? The things we concerns is what? Is the differences, right? So the differences between the two treatments is our concern, right? So like in here, the new drug and the new pain relief medicine, and the new pain reliever medicines here. I want to see is the new one and the old one, they really make a difference or not, right? So the differences between these two treatments is really what will concern. So like in here, you say, okay, so now, you know, we have old and the new, so you can find the differences here, right? This is a difference 1, this is a difference 2, this is a difference 3, da da da, to the difference maybe ends here. So in fact, because we're only concerned about the differences, so even I have 2 set of the observation, so really we end up with what? We really end up with 1 data set. Right? So this data set is the differences. Okay, so because this is 1 data set and it's the differences here, so based on what with the hypothesis we did before, so what type of the, you know, what type of the test we're going to use? We're going to use what? So we're going to use the t-test here. Okay, so that is the why. So in the pair T, so in here, instead of just say t-test, so we give a specific name, we said it's the pair T test. Okay, so we call it the pair T test. Okay, so we call it, this is the pair T test. Okay, so the reason why it's a pair, because we combined 2 sets of the observation into 1. The reason why we can combine that is because we are dealing with the 1 similar population, right? So we are trying to find the before and after we apply the 2 different treatments, you know, in the same objects. Here is new and old. Okay, so we know is we're going to use the pair T test. So what are the assumptions here? So the assumption here is very similar like what we talked about in the t-test before, right? So the assumptions here, the first here, they have to be paired, right? So that's obviously, so we know the data must be what? Must be paired, right? So that's why we choose the pair t-test. So when you read the problem, so for example, let's say I take 10 patients from the hospital A, and I take 10 patients from the hospital B. One I give an old drug, and one I give a new drug. Obviously, this is not paired, right? This is 2 independent samples, right? One is from the hospital A, and the other is from the hospital B here, right? So then we say, okay, this data is not paired. Okay, so that's why we said the first thing is we need to make sure we fully understand what is the meaning of the pairs, right? So that means the same object, you have 2 treatments, right? So that's why, in fact, you really have the 1 set of the objects, but then you apply the 2 different treatments to each one here. Okay, so now the independence assumption, just like the t-test. So we said observation, they have to be independent. Because in here, we only care about the differences here. So we say the differences here, okay, must be independent of each other. Okay, so that means in here, so like we talked before, so like one patient, you know, his relief is 8 minutes and 6 minutes. The second patient is 12 minutes and 10 minutes. So the difference is all 2, but those 2, they are what? They are independent, right? So this patient and this patient, they are independent. They don't, you know, they don't have a relation. That's what we mean, the independence assumption. That means to apply the differences here, they must be also what? The differences here must also be independent here. Okay, so the randomization is when the data was, so we need to randomize the way we collect the data. So we need to randomize the way for data collection. Okay, so like for example, when you said, okay, I have like these 10 patients here, right? So I will give them the older medicine first. So you can randomly pick and say, okay, this patient, I will give you the older medicine, and this patient, I will give you older medicine. So you are doing a randomly orders here. Then when you apply them to the new medicine, the same group of the people, then you randomly kind of the select, say, hey, this one, I give you the new medicine here. Maybe this is the first one, I give you the new medicine, then this one, I give you the new medicine here, right? So maybe, maybe the time of I give the medicine, sometimes I can give it in the morning, I can give it in the noon, I can give it in the evenings, right? So when you give them the old medicine, you randomly pick which one they receive in the morning, which one they receive in the afternoon, which one they receive in the evening. And then when you give them the new medicine, you do another randomizations here, right? So you do a set of, so for the first one, maybe you give them in the morning, then for the older one, then maybe the next time when you randomly pick, you will give them during the evenings, right? So that's what we say, we want to randomize the data collection. So you need to be careful. You don't want to have a systematic issues, right? So you don't want to say for the first persons here, maybe first person is good in the morning, right? So then the next time, maybe you want to see how is the new medicine work, if I give you in the evening, because in the real life, you have no control which, like give you in the morning or give you in the evenings, right? So that's why we said randomizations conditions here. So then the next ones here is the 10% conditions here. This is the same as the t-test, right? So that means your sample size, so the sample size, you want to lessen the 10% of your population, right? So now in here, you want to make sure you don't want to because the whole population, if is very small, then we need to be very careful here. Then the normal conditions here. So it's just, when we talk about the t-test, we said the data has to come from a normal distribution. So in here, we do the same ways here. So we say that the differences here, right? So we say the differences here must follow the normal distribution. And we know sometimes, it's not going to happen here, okay? So if you cannot really test it, then you can use the histogram, okay? Or something we call this normal probability plot. So get the eyeball of the data, right? So to get near, we call this the near normal situation. So as long as, the data, was not deviated too much from the normal, then we know from the previously, so our t-test will work out pretty good here. All right. Okay, so now for the pair t-test hypothesis, remember, right? So we are care about is what is the differences here, correct? All right, so now our hypothesis here will just be the H0s here. We use this notation is mu, the differences here is equal to, we say, it's data 0. Typical here, we will say data 0. Typical, we will say delta 0 is equal to 0. That means there's no differences, right? So what is the mu? What is this mu d? The mu d, that means you have, we said before, you have like this is before and this is after, right? So each one you will have a different observations, right? So here we said in here, you said you have different observations here. Then for each observation, then you minus it, you get the differences of 1, differences 2, differences 3, and the differences ends here. So I want to test my differences, are they equal to 0 or not? If they are equal to 0, that means no differences, right? The differences is it's not exist or is very, very small, right? So it's no differences. So also we can have, we said mu d is greater than, okay, so let's do like what we always did. So we will set a two-tail test, right? So we will set mu d is not equal to delta 0, or we said mu d is greater than delta 0, and we said mu d is less than delta 0. So it's really depend on how do you want to define the UD. You just need to be consistent, right? So you can use the after minus before, or you can use before minus. It doesn't matter. And then according to the problem, right? Based on what the problem asks you, say, is before better than after? Then if you use the U before, if you use the before to minus after, if you define that this is your D, if you use before to minus after, and then if the problem asks you, is before is better, right? Then if it asks you is better, so which one you choose? You choose this one here, right? Because it's better, that means it's greater than zeros, right? So that's why, that depends on what is the problem and how do you define it, right? So the differences, you could use the after minus before, or before after minus the after, but then you test the statistics and your alternative hypothesis the way you choose it need to be consistent with what your problem want, right? So then the same things here, we have we call this the two tails, right? Just like we did before. And this one's here is here, and this one's here is here. Okay, and then the test statistics here. So the test statistic will just be we say it's the t-test, because the populations sigma is unknown, because I don't know what is the population sigmas here. Okay, so the t-test here will just be your average, all this D here. So you say the D, we put is D average. Then minus whatever the delta you try to test, correct? So the delta you try to test is delta 0, so you minus delta 0. If you try to test the mu D equal to 0 or not, then you just test 0. And then the denominator will just be the standard deviation of the D. So the SD, this is equal to the standard deviation of the differences. Okay, and then just like before, divided by the square roots of the ends here. Okay, and now in here we said, okay, if I want to find the critical value, so we know the D distributions always have a degrees of the freedom. So the degrees of the freedom, as we know, we talk about it when we test the two populations, right? So it's N1 plus N2 minus 2. But in here, right, so this is really is one group. And I'm only care, because this is a pair, I'm only care about the differences here. So in fact, I only have how many set? The data, I only have n's, right? So that's why my degrees freedom is what? Is a minus ones here. So this is very important, right? So because it's not N1 plus N2 minus 2, because I only have one set of the data, and this set of the data is the differences, and that is the differences, is what we are care about. Okay, so now the last things here before we finish these videos here. The next video, we're going to focus on how to use the TI-84 calculator, the R, try to do the test statistic, find the p-value. So let's just take a look at what we call is the blockings here, right? You know, like when we talk about the blocking things here, so we talk about the effect, right? So the blocking here. So for example, for the blocking, for example, if we paired every house families, right? So if we paired the husband and the wife. Okay, so if we pair the husband and wife, and we want to find the differences in the ages here, okay? So obviously, the differences in the age. So this is one family. Yeah, each family I paired the husband and wife. Each family I paired the husband and the wife. So like if you want, one of the wrong way. People say, oh, you told me from the previous lecture. We say we do a box plot, right? So in here, if you say, okay, I'm going to do a box plot here. All right. So if you do a box plot in here, so you will see here. So if this is the wife's age, and then the same way you can do a box plot here. You will say this is the husband's age. If you treat it as two groups, then you will know there's not much differences between the wife and the husband, because in each family hold, the wife and the husband, their age is related. Okay, of course you can have a 70 years old man and marry a 50 years old woman, or a 70 years old woman marry a 50 years old man. So they are, but the majority, the age differences is maybe in the 4 to 6 years differences. So now if you graph the histogram, okay, so this is the age differences here. Okay, and so now this here, this is the numbers of couples. So for these things here, it makes more sense here. So if you plot the histogram, okay, so then probably this is a 0, this is a 4, something like that. So then this graph make way more sense than this ones here. The box plot here does not serve the purpose here. Sometimes will mislead you. Then you got to say the wife and husband, they have the same range. But remember, so we are specifically choose each families, right? We pair the husband and the wife. So this blocking effect here, right? So most of the time, if you do a box plot, you cannot really see that. Okay, so that's why, this is a come to say what, when we do that, what can be wrong here. Okay, so the biggest differences, what can go wrong, the biggest problem for a lot of people is use the two simple t-test instead of the pair t here. All right, so make sure the first things here, don't make this mistake. Do not use too simple t-test for the pair data. Okay, right? Okay, so other way backward here also is the same. We say don't use the pair t-test when the samples is not paired, right? So like the example we talk about, I have the hospital A and hospital B. Okay, so if I take 10 patients from hospital A and I take 10 patients from hospital B, Even they both have 10 patients I take, but you cannot pair them, right? So that you cannot use the pair t-test here, okay? So also the next things here is don't forget about the what? Don't forget about the outlier. Okay, so of course in this outlier now, what do we care? So we cared is what? Is the differences outlier. Okay. So from the wife and the husband, I might have a family I choose, they both in their hundreds, right? So, but the differences, maybe they are only different by 2 years. So that's not an outlier. So now I'm clear about the outlier is in the differences. So when I find the differences is the outlier, okay? Okay, so we said don't look at the differences between the mean on pair group by using the side-by-side box plot. Yeah, that is really very misleading here, right? So just like we say here, it's because each pair, if they that's what is the pair mean. They relate to each other. So the two observations, they relate to each other. So this we said, the box plot, we said this, we said it before, we said that this box plot in our previous lecture number 8, we said the box plot is the good things, right? We want to do it first when we do the what? When we try to compare the two samples here. Okay, so that's the big difference. So when we kind of compare the two samples means here, we say the box plot is good here, right? But now for the pair, if you try to, try to graph the blocking effect, and they're going to have the blocking. So that because each pair, right, they are related. Okay, so but if you separate them up, you really did not get any useful information, and also sometimes very misleading here. Okay, now let's stop here for this lecture, and then our second video we're going to take a look at the example, and then we're going to take a look how do we going to use our TI-84 calculator to help us to do this. Okay, so it's a good time to take a break here. Okay, talk to you later. Okay, bye-bye.